Hello everyone. In the previous video we have actually discussed Ampere Circuital Law. We have seen one application of Ampere Circuital Law where we have calculated the magnetic field at a point due to a straight current carrying conductor. Now we will see one more application of Ampere Circuital Law, that is to find the magnetic field due to a current carrying solid cylinder. Now we are considering solid cylinder. It can be a wire also, but we will consider the position of the point, that is where we are going to calculate the magnetic field, once outside the cylinder and then inside the cylinder also. So there are two different positions in which we can actually find the magnetic field. So let us see how it can be done. Here you can see we are considering a cylinder. It is a conductor only. We can consider it to be a straight conductor which is cylindrical in shape. It can be a wire also, where a current I, you can see here, small I represents the current which flows in the direction as shown here. Now the radius of the cylinder is capital R. This is solid, that is it is filled from inside, and it has a radius which is given by capital R. Now in such a situation where the radius is given as capital R, this is the radius, I am drawing the radius here, so this is capital R. Now you have to find the magnetic field by using Ampere Circuital Law at a point outside. Suppose you consider this point outside, and at a point inside the cylinder also. So there can be different points. You can have the point inside also, you can have the point outside also. Now if you see the cylinder from the top, that is your view is as shown by the arrow, that is the top view, then we have a separate diagram on the right for the top view. And if you see it from the top, you can see here, this is the center of the cylinder. This represents the radius R. Now a point can be considered outside the cylinder and a point can be considered inside the cylinder. Now we have to use the Ampere Circuital Law, and we all know, like using Ampere Circuital Law, it is required that we need a closed loop. So when the point will be inside the cylinder, we will have a closed loop as shown here. The radius of the Amperian loop will be given by small r, and when the point is outside, then the radius again will be given by small r only. So small r represents the radius of the Amperian loop in all the conditions. Now let us consider both the conditions one by one. First of all, we will consider the condition where the point is taken inside the cylinder. Okay, so when the point is inside the solid cylinder, see, when the point is inside the solid cylinder, the Amperian loop, this is the Amperian loop which we are considering because the point is inside the cylinder. The radius is from this point to this point. This is the cylinder radius of the cylinder, which is given by capital R, whereas the radius of the Amperian loop will be given by small r, which is less than capital R. Okay, so that is the point which you need to understand. So here the condition which we are taking, that is the radius of the Amperian loop, small r, is less than the radius of the cylinder, which is given by capital R. Now the current I is distributed uniformly throughout the area here. The area of the cylinder, the cross-sectional area of the cylinder will be given by pi into capital R square. The current I is distributed uniformly, and the current I is in the upward direction. If you take the top view, then the current will be in the outward direction, that is towards you. Now we will use the Ampere Circuital Law, which says that integration B dot dl is equal to mu naught into the total current threading the loop. Okay. Now in the left hand side we have written integration B dot dl over a closed loop is equal to mu naught into the total current which threads the loop. Now you can see here the loop is having radius smaller than the actual radius of the cylinder. So the total current which comes out through the cross section of the cylinder is I, but through this Amperian loop it will be less than I. So we need to find the value of that current which passes through or which threads through this Amperian surface. So first of all we will find the current per unit area of the cylinder. Total current is I and the total cross sectional area is pi capital R square. So this value represents current per unit area. Now if this is the value of current per unit area, then the area of the Amperian loop is given by pi R square. Now the current per unit area is given by I by pi capital R square. So if we multiply it, we will get the current which passes through or threads through this Amperian loop. So the value of current, the pi cancels out here, and accordingly we can have the values. Now on the other side, that is in the left hand side, you can see B dot dl. Now magnetic field, we know that for this conductor the magnetic field will be in this direction, and dl, the small length of the Amperian loop, this both will be in the same direction, so the angle between them is 0. So B dot dl will be B dl cos 0. So B comes out, integration dl, and the integration dl, the total length or the total circumference of the Amperian loop will be 2 pi r. So B into 2 pi r, which we are getting. So from this we can calculate the value of B. 2 pi r moves to the other side, that is the right hand side in the denominator, and these values of pi cancels out, and small r also, 1 square will cancel out, and finally we have this value which is B is equal to mu naught by 2 pi I small r upon capital R square. Now here all the terms are constant quantity except this small r, and the variation of small r, because we are choosing a point inside the cylinder, so the variation of small r will be from 0 to capital R. So we can write here that the magnetic field B is directly proportional to small r, and small r is the distance from the center. So I hope this is very clear to you. So we move to the next point now, and the next point is we are going to find the magnetic field at a point outside the solid cylinder. So let us see how it can be done. You can see here we are going to do that when the point is outside the solid cylinder. Again, same diagram we are taking. Now this time the point is outside. Suppose the point is here. Now if the point is here, then the value of this radius of the Amperian loop is small r, which is greater than capital R. Small r is greater than capital R because the point is outside, so the radius of the Amperian loop is greater than the actual radius. So if this is the condition, then we will again use the Ampere Circuital Law. Integration B dot dl over the closed surface is equal to mu naught into the total current threading the loop. Now this time you see, we know that the total current threading which the conductor carries, that is through the cross section, the whole of the current is threading through the Amperian loop. This is the Amperian loop which we are considering here. So threading through the whole Amperian loop. So the total current is I. So it is B dot dl is equal to mu naught into the total current, which is I. Now again, B dot dl, we know that the direction of B and the direction of dl, they are same for this conductor. B and dl will be tangential to the Amperian loop. So B dl cos 0. So B comes out, integration dl is 2 pi r, which is equal to mu naught I. And so finally we get the value of B, which is given by mu naught by 2 pi I upon r. This is the same value which we have considered, or which we have actually derived for a straight current carrying conductor. The magnetic field at a point at a distance r for a straight current carrying conductor, which is infinitely long. Now here we can see that the magnetic field B is inversely proportional to the distance, because in this quantity this is the variable only, small r, and as we move away from the cylinder, the small r increases. The variation of small r will be from capital R to infinity, and as we move on, the value of B decreases exponentially. So negative exponential curve will be there. So I hope both the conditions are clear. First of all, we have considered the point to be inside the cylinder, and secondly we have considered the point to be outside the cylinder. Now let us draw a graph which shows the variation of this magnetic field as a distance from the center, which is given by small r. So let us see that how it will be done. Look at the graph here. When the value of small r at this region, when the value of small r is less than capital R, that is, the point is inside the cylinder, at that time we have seen that the value of magnetic field is directly proportional to r. So that's why we get a straight line up to the point capital R, which is the radius of the cylinder. And outside, where the value of small r is greater than capital R, that is, the point is outside the cylinder, at that time it decreases exponentially. B is inversely proportional to r. So we have a curve like this. At the point where the value of small r, that is the Amperian loop, radius of the Amperian loop, is equal to the actual radius of the cylinder, we get a constant value which is given by mu naught I by 2 pi capital R. Here nothing is variable, so this is a constant value. So I hope this is very clear to you. Any doubt, you can post me the doubts and it will be solved as soon as possible. So don't hesitate to post me the doubts, if any. Thank you.